I'm glad I didn't have to say applause then. I like you guys a lot this year. All right, so Walter, take it away.
I'm going to talk about an AArch64 code generator. I do not know why they call it Arch instead of ARM, but whatever. So who thinks this is a really dumb idea? So what the heck am I doing thinking about writing a AArch64 code generator? Well, I do agree it's a bad idea because, we already have two fine professional compilers working on the ARM. Why am I bothering to do this? But I'm going to do it anyway. I've implemented code generators for the x86 family, as you all know. How many of us are on the spectrum? I definitely am. My whole family is. I was in the grocery store once, and one of the guy who was putting groceries in the bag asked very quietly to me, he says, "Are you on the spectrum?" I said, "Oh yeah, my whole family is." So anyhow, DMD's code generator does have some advantages. For one thing, it's very fast. It turns out that DMD has kind of fallen into a niche of when you want to do rapid development of your algorithm and code, having a fast compiler is a big deal, and DMD fits the trick. The other thing is, you're not really a compiler writer if you haven't written a code generator. Now, there's been an explosion of languages since the optimizer and a code generator was kind of outsourced to free software. So anybody and everyone can write a language. And one thing that's not well known, it's not that hard to write a code generator. A lot of people think it's some deep, mysterious thing, but it's not. I've done crazy things before. Writing a C compiler into the D compiler was not a popular idea. People suggested I should focus on something useful. And it turned out that it had a lot of really neat consequences. One of the most interesting ones was and this was discovered, I swear, I did not think of it. It did not even occur to me. I think it was Stephen who discovered that you could use it to convert C code to D code. Who would have thought that that was something that would just fall out? So it turned out to be very valuable, and import C turned out to be a very useful thing. So, sometimes I do things that other people think are crazy and they work out okay anyway, but that's not a guarantee that this is going to work. Okay, I'm a nerd. I've already admitted that. And this is going to be fun because I like writing code generators. It's just fun. And I want to do it by adapting the existing code generator. I'm going to say that sort of a precursor to this talk is the one I gave last year about how the code generator works. So I don't want to repeat myself. So I'm going to be kind of assuming that you've all seen that. I want to reuse and recycle as much of the existing code generator as possible, which means looking through the various sections of it, there are parts I can recycle from the x86-64 code generator with almost no changes. Things like the register allocator. It turned out that that was very adaptable. The general layout and how it operated, how it dealt with common sub-expressions, the stack layout turned out to not be quite the same. Because of the way the instruction set works on the ARM, you kind of want to do it differently than on the x86. The intermediate code is the same. The object file generation is the same. And the existing test suite. A lot of people underestimate how valuable a test suite is. Well, I've been running our test suite on the new AArch64 code generator, and it's finding an awful lot of bugs. So the test suite is doing its job and is an invaluable asset. I started on this knowing nothing at all about the AArch64, except it was a 32-bit risky architecture. And no matter how many times I read through my slides, I still forgot to insert the picture that goes with this. Doesn't really matter. What I did was I bought a couple of books on, how to write assembly language for the ARM. And those books turned out to be useless because they didn't really explain anything about it. Things I don't need from the existing code generator is made an executive decision that 32 bits are the best, so I'm not going to bother with that. Of course, I don't need XMM instructions. The more interesting thing here is the AArch64 instruction set. The only thing it does with memory is reads it or writes it. It never does a read write on a memory location. So a large chunk of what's in the detail of the x86-64 can just be skipped. There's a lot of kludge instructions in the x86 that we can get rid of, like the wacky string instructions. There are several different methods of passing parameters to functions. Fortunately, with AArch64, there's only one way to do it, so that simplifies things. On the x86, the floating point FPU cannot talk to the registers, so it would have a fake floating point register that can be used to transfer data between the floating point unit and the arithmetic unit. Don't need that anymore. And the last one is who doesn't know what the LEA instruction does? Okay, the LEA means load effective address, and the hardware has a heavily optimized microcode or whatever is going on inside the chip that makes it very fast. So certain kinds of arithmetic instructions can be executed very quickly with an LEA instruction rather than doing a separate multiply add. So that optimization is actually used all over the place, and I can just snip that out because that kind of instruction doesn't exist. Some things we can't leave behind as complex numbers. That's going to cause me a bunch of trouble because the complex numbers seem to require a lot of implementation effort. And I'd rather everything was switched over to using the import of complex numbers, but that turns out to be impractical because of import C. So import C is kind of holding me back. I'm still going to have to implement complex numbers in the back end. Okay, godbolt.org is God's gift to or compiler developers, and who never thought it was useful for compiler development? Turns out it's extremely useful because I didn't know how the instruction set works. So I would spend a lot of time writing one-line functions and run it through Godbolt and see what instructions dropped out the other end. One thing I really like about Godbolt is not only does it give the mnemonics, it gives you the hex bit pattern. Now, why would I be interested in a hex bit pattern? The reason is the STR mnemonic has a large number of implementations of it in hardware, all with different bit patterns. And so that was one thing wrong with the hobbyist books is they would have these STR instructions. By the way, STR means store register contents to memory. I couldn't tell which one it was, and it didn't give me the hex dump. So the books are useless. Anybody love fiddling around with 32-bit hex numbers? You take the small font on the screen and those hex numbers, and it makes my eyes bleed looking at those hex things. I was desperate to find a better way to deal with this than deal with hex bit numbers. So the idea was the first thing to create was a disassembler, which would read those awful hex numbers and would produce the mnemonics out of it. This is all built into the compiler. If you compile with the -VASM switch, it will not present to you the generated instruction mnemonics. What it does is it takes the actual binary generated by the compiler and disassembles the binary. So that way, it's a wonderful way to check that it's generating the right hex numbers and I know which instruction it is. So I did that part. Also put it into my object file disassembler. Now, there already is a disassembler as one of the usual tools that come with your dev system, but I wanted to write my own disassembler as a great way to understand the instruction set. Now I have the tools. I can convert binary to assembler because with the Godbolt thing, I'll take that hex value and just type it in. My program will give out the correct assembler for it. Binary, I can also go to the specification URL. It turns out the AArch64 specification is online. Spec URL is the binary. But the only thing I'm missing in all this is going from assembler mnemonics to binary, which needs an inline assembler, and I have not written that yet. And I believe Emmanuel is working on creating one. I thought many times I should stop and build that inline assembler because it will speed up the backend development, but finally decided not to do that. It turns out that the AArch64 is not a simple instruction set in any way, shape, or form. I programmed the PDP-11 back in the old days, and the entire instruction set fits on one 8.5 by 11 sheet of paper. The whole darn thing, including the floating point instructions. There was something like 2,000 instructions in the AArch64, and there's not much of a pattern to it. It all looks like, how evolution does not create anything in an organized fashion. It's just everything is a massive kludge that's adapted to do something else. Like our hands and fingers are actually flippers that were readapted to be fingers. And that's what the AArch64 thing looks like to me. Fortunately, it's divided up into groups, which have a specific bit pattern. Those bit patterns have variable parts, and those are the individual instructions. So you have a tree that's 2 layers. There's the group and then the instruction. And the end result is generating a 32-bit value. So here's an example of a group, the LDST_pos group. And those are the list of instructions it generates. And if you look at the bit pattern at the top, some of the bits are fixed and some are variable. And with the fixed bits, that sort of defines the group. And if you'll notice, none of those bits line up on hex boundaries, which makes working with the hex numbers, I can see Marty is squinting at the screen. I know exactly what you're thinking. You're going, my eyes are bleeding and looking at those bit patterns. And I would actually write it on graph paper, the bit patterns. I would take the hex and manually convert it to bits, and then I would hold it up to the screen and try to line it up with the whole thing sounds stupid, but it was agonizing. So I wrote functions that would match what the spec called it. I wrote a function called LDSTPOS, which has arguments which are all the variable parts of the instruction, and then it assembles the instruction out of the bits. And here's one of the stir fpsymd, which is a store immediate floating point value. That sort of refines the bit patterns to a smaller subset, and still with some variable aspects to it. And this one, the size of the operands and an offset and a source register and a destination register. And so we have another function, stir fpsymd, with those variable bits to it, which then it adds extra bits and calls LDSTPOS. So why did I do it this way? And that's because the names of the functions line up with the URLs in the spec. I guarantee you will be driven mad if they don't line up. So one feature of Godbolt that is missing is for each instruction, there should be a link to the spec page for that function. But Godbolt is missing that, so I wrote my own in the disassembler. It will not only give you the opcodes, it will give you the URL to the spec page, which turns out to be extremely valuable and an enormous time saver. The disassembler just simply does that whole thing in reverse. You give it a bit pattern, and it checks the load store register group, which is the LDSTPOS, and then the specifics for each of the instructions are decoded from the field, and it then prints out a string. You don't need to read the code. That's not the point of the slide, just sort of what the purpose of this function is. Now we get to some of the dirty details. Registers. Everything in the x86-64 code generator fit in a 32-bit bit mask. So all the register allocation, all the tracking of register contents fit in 32 bits. It actually worked out extremely efficiently. The register allocator works that way. The selection of registers for arguments on the stack works that way. Everything works that way. So I wanted to continue with that. And the problem I ran into was there are 3 register sets in the AArch64. The first 32 are the general purpose registers. The second 32 are the floating point registers. And the third 32 are the 128-bit registers. The floating point and the general purpose register masks are disjoint. There's no overlap. My first step was I had to increase the register mask to be 64 bits. And that actually enabled me to use more registers that were now available in the x86-64 code generator. There are a few special values in there, like there's the FPU top of the stack. PSW is the status word. No reg means it not a register. Underneath that is a list of the AArch64 general purpose registers and what they do. It came right out of the spec. And then the floating point registers. The important thing here is the V8 to V15 floating point registers are callee saved registers. Oh, this AI image generation is fun. Draw me a picture of floating point, and that's what I got. Okay, the types are 6 that I'm going to support. Well, not quite yet. You have the 16, 32, 64, 128, and that's the half float type. Sorry about that. I had to do that. Every time I see half float, I think, hobbits. 16-bit floats are not supported by D, but they are well supported by other AArch64 compilers. So we're going to have to modify D to support 16-bit floating point types. Fortunately, it falls out of the instruction set. So as I go, I just have the backend supported, even though there's no support elsewhere in the compiler. Then there's a Q factor. Remember I said the 128-bit floating point registers. Well, they actually do overlap with the general purpose floating point registers. So now I'm stuck. For the calling convention, only the floating point, the bottom 64 bits of it are saved, and the top is not. So that means that every time you call a function, your Q registers are going to have the top half of it trashed. So how do I deal with that when my register mask cannot distinguish between the regular size floating point registers and the long ones? And I thought, I'm in deep trouble with this. And then I kind of had an epiphany, as the only problem is the floating point registers that are supposed to be saved when you do a function call. And I go, what if I just simply do not use those registers for the Q registers? And yes, I give up 8 registers, but the whole thing works. And it's not like I haven't done this before, because not all the registers on the x86-64 are available because they don't fit in the register mask either. So I think this is a reasonable compromise. Also, it turns out that the AArch64 has no instructions for the 128-bit floating point except load and store, so everything has to be done as library functions. And I plan to use the existing library functions to implement it. Function calls, fortunately, there's only one function call sequence to deal with it. Interestingly, it's very much like the Windows 64-bit function call syntax. So the neat thing is I already have the code to make that work in the code generator. So ta-da! It's kind of fun. You can pull various pieces out from the various code generators and patch it together, and you have an AArch64 code generator.
If you could go one slide back, is that meant to say by value?
What?
Because using structs less than 2 registers are passed by reference and larger structs are passed by pointer.
Oh.
That seems odd.
Well, you are correct. It's embarrassing how many times I go over the slides and wind up with the inverse of what I meant, but very good catch. Unless they have constructors, then they're passed by ref. The people who come up with how to deal with variadic function calls, I think their motive is to punish anyone who uses variadic argument lists. You get this ridiculous amount of code generated just to deal with it. And even worse is every platform and every compiler has a different scheme for it. They can't decide on, we're going to follow this scheme. You don't really need to understand this. This is stuff I have to deal with. I just wanted to show what the complexity of it is. And you'll see the code that reads these data structures is in the varargs.d import. And here's the kind of code it generates. Every time you have a variadic function body, this is kind of what you get. The code generator code to do that is, I hate it. It's ugly. I can't think of a better way to do it. Unfortunately, the kludginess of the instruction set shows up as the kludginess in the code generator. Okay, now we're getting into some differences between the instruction sets that matter. The x86-64 literal encoding is done using variable length instructions. So x86-64, there are instructions to load an 8-bit value, a 16-bit value, a 32-bit value, and a 64-bit value. All have different encodings, and it's all done in line. Floating point constants are loaded from memory because there are no floating point instructions that have embedded floating point values. Literals and addresses can be easily coded into the instruction. So we have the AArch64 literal encoding problem. 64-bit address does not fit in 32 bits. A 32-bit value does not fit in a 32-bit instruction, neither does a 64-bit value, and a floating point value does not fit into an instruction. So even though all the instructions are 32 bits, there's, well, I wonder how they deal with this problem. Of course, God bolt to the rescue. I said earlier that the AArch64 was a very complicated instruction set. And it's complicated, weird, and wacky in a completely orthogonal way to the weird and wacky x86 64-bit instruction set. So I kind of think they fail to actually improve it. It's just different. My favorite, of course, is the PDP-11 instruction set, which figured out how to do literal encodings in a completely, extremely simple manner. But that's why the PDP-11 instruction set is a gem that has never been equaled or exceeded. So it turns out what you wind up with is multiple kinds of instructions depending on what your integer value is. There is no instruction to load an integer value. What there is an OR instruction. You OR it with 0. The W31 is usually the stack pointer, but it turns out you never need to OR the stack pointer with everything. In the AArch64 instruction set, the stack pointer is actually interpreted as the value 0. They can get rid of a load of a value by simply ORing it with 0, which I reluctantly admit is very clever. Wish I had thought of that. So 0, of course, does fit into 32 bits. So does 1, 2, 3, 4, 5. Well, that fits into 32 bits. But what are you going to do with large values like negative numbers? Well, it turns out there's an instruction called move negate. So now you can have small negative values that will also fit in 32 bits because the instruction negates them. But that's not a complete solution. And at some point, you're going to have to use 2 instructions to load a value. Now, I was puzzled when I was first reading the instruction set is why is there's this load an immediate immediate value that is shifted left then by 16 bits. Well, I found out why. You have to have 2 instructions. One is the bottom half, and then the other OR's in the top half, shifted left by 16 bits. And oh, by the way, it can also be negated, shift left by 16 bits. I had to write this function, which is load a immediate value into a register, and it figures out the optimal sequence of, which instructions are going to get me into the register the value I want. Some of those are very complicated, and it took me a long time to figure out how the algorithm to generate an immediate value actually worked so I could implement it. Floating point literals. I was looking at that and looking at it, and finally I figured out what was going on. The floating point literal is encoded as an 8-bit floating point value. Now, how many people work with 8-bit floating point values? They actually seem to be used in some AI things for the weighting. Well, anyhow, you have 8 bits, so you have a sign bit, 3 bits for the exponent, 3 bits for the mantissa. And it turns out that most floating point constants fit into that form rather naturally. So this is fairly efficient. But if you want more complicated ones, the only way to get them in is to load them from memory. So that requires 2 instructions to do it. The first one loads part of the address into the register. And the second instruction loads indirectly through the first address and adds another constant in. And those AArch64 things are called fix-ups, and those are replaced by the actual location of the floating point constant. Doesn't that just make you happy seeing that? This is what you need Godbolt for, because Godbolt will actually, in its disassembly, point out what the relocations you need are. It turned out that I had to spend an hour trying to figure out what are the relocations for the AArch64, and I would see all these descriptions of them, but none of them ever gave the values for the fix-ups, and so I'm still working on that. That's why I need a disassembler. Taking the address of something is something similar. It's also done with 2 instructions with 2 fix-ups. And notice the LO12 as part of it. There's the high 21 and then the LO12. Well, you can guess what that is. One gives 12 bits and the other gives the next 12 bits. Current state of play. My first target was the Raspberry Pi because I'd had that for years and never found a use for it. And I finally found a use for it, which was generating a code generator for it. So I've been working on that and actually got a bunch of programs to compile and run on the Raspberry Pi. I don't think that's really going to work as a target. So in the last week, I bought myself a new Mac Mini and spent 3 days trying to get it to compile anything. So I'll be working on that from now on. And that's the new target. I have not implemented complex numbers. I have not implemented SIMD. I don't know how any of those instructions work yet. I have a partial implementation of half floats, no inline assembler. My goal is to get it to work and not pay any attention to optimization. You can really go down a bad path if you start optimizing too soon. And there's also the implementation problem of the 128-bit floats. It turns out that mastering the instruction set is not very easy because although you can understand the bit patterns, how the instructions play together is not really easy to figure out. And that's where Godbolt comes in. Having an existing code generator that I can reuse much of has been a great accelerant for getting this done. So I guess we have time for questions. Thank you.
Yeah, I wonder if you have a SIMD support with the Neon extension, you could have floating point 128-bit arithmetic with those instructions. Is it possible to do without the functions that you implemented?
Yes, because, well, that's also possible with the SIMD instructions on the x86-64, but it's done with completely separate code because although it's the same idea, it's a totally different scheme used with it. I don't really know anything about the Neon instruction set. It's just I'm not going to worry about it till everything else works, but I will make it work one way or another. If I beat my head on the wall long enough, I will eventually figure out a way to make it work, just like I did with those Q registers.
Or if you getting to be able to compile DMD with itself on AArch64.
Okay, here's the order in which things go. One is to get hello world to compile and run, and yay, we've got that working. So the next thing I've been doing is trying to compile the test suite, not run it, just get it to compile. And you'll find, well, I find all kinds of things I've missed. So the test suite is invaluable. Once that works, then I need to get the runtime to compile. Not going to try to execute it, just get it to compile without error. Once then I've got that thing working, then the thing to do is, and this is why I've been so adamant about the test suite not requiring Phobos to work, is then I can start running the test suite with the compiler. Once the test suite passes, then I go to Phobos and get Phobos to work. Once I get Phobos to work, then I can get the compiler bootstrapped on it. So I've done that order before. It works. It's the most straightforward way to do it. If you try to do everything at once, you're just in for nothing but misery.
My main rig is a Windows ARM64 machine, and once you've done all of that, could you please add the ARM64X linker format and ARM64E code gen, which is a way to mix and match x86 function and AArch64?
Oh,
The same binary, because the Windows situation is quite complicated.
Oh, that doesn't sound enticing at all. Unfortunately, because it sounds like a major project, I don't want it to interfere with getting the rest of this language to work. So yes, I want to do Windows support, obviously. I want to do Linux support, obviously, but it's kind of a critical thing getting the Mac stuff to work because right now it's working in emulator mode, which cuts its speed in half. And I know that the Intel architecture seems to have reached a dead end. And if DMD is going to survive, it needs to support the AArch64.
Okay, this is not a question, but in the beginning you said we don't know why it's called AArch64. I asked an AI about it. I don't have a site for this, but I believe it 100%. So if you compare it with x86, you have the Pentium, the 386, which is an x86, and then you have the core 2. But if you look at ARM, you have ARM4, ARM5, ARM6, ARM8. And it would have been very weird to say, now we have ARM8, which is ARM64.
Okay, yeah, that makes sense. Yeah, the nomenclature for the x86 family tree is completely crazy. So they failed to avoid that with the the AArch64. They walked into the same tar pit.
I think in addition to Windows, Mac also has universal binaries that work with x86 and ARM. So I'm not sure if that's on your roadmap as well.
I did not know about that. I don't know even if that's a compiler feature. It may be a linker feature.
It could be a linker feature. I'm not sure.
Yeah, if it's a linker feature, I'm not going to worry about it. Linkers are supposed to be simple programs, and for the original PC, they were trivial programs, and they've just turned into these monsters.
I think that the RISC-V would be easier.
The what?
RISC-V would be easier than this.
I don't know anything about the RISC-V.
I have been working with the MIPS architecture, which is very similar, with also having 32-bit instructions and loading immediate values with first the upper half and then the ORing in the lower half or something. As far as I know, that's because there's a fixed instruction size, so you cannot fit a 32-bit immediate value in a 32-bit instruction because there's no opcode left.
But you can do it on the PDP-11.
So I was wondering, how does the PDP-11 do it? Does it have variable instruction length, or does it have some genius way? Or
it has some genius way, which is why the PDP-11 is the greatest instruction set ever. The program counter is a general purpose register, which means that you can move values into it. You can increment it. You can auto increment it. So you know where I'm getting at? What happens when your source operand is the program counter auto incremented? It reads the next 32-bit value out of the instruction scheme. So it requires, things like, branching to the thing require no new opcodes, because the branch is just simply moves the program counter into, or moves the target value into the program counter.
the immediate value is kind of intertwined with the instructions, and with clever program counter manipulation, you read it and then continue. Oh, that's actually, I have never.
It's brilliant. And if you look at the assembler books, you don't see any of that. You just see move this register, this value. And under the hood, the macro assembler generates the extra things, but it's not actually a separate instruction. The pre-increment and pre-decrement, post-increment work their way into the C programming language, as we all know, was the plus and minus one. So that's where it all came from. It came from the 11 instruction set.
I want to study that instruction set now.
Okay, well, I'll send you a copy of the one page. You're looking to go, oh my God, this is so simple. Oh, the PDP-10 had an even funner one. They saved on addressing modes by the bottom 16 memory locations was the CPU register set. So if you wanted your code to be really fast, you fixed it so it fit in the registers, then you execute the registers. It's too bad all that stuff has died and disappeared. Yeah. People always say, when they developed the 68,000, oh, we're building an 11-like instruction set. And no, that's not 11-like. It's they couldn't help but try to fix it, and they made a mess out of it.
Walter, you know why the PC is a general purpose register isn't a great idea in terms of making things go fast. I mean, basically, it creates havoc in the microarchitecture. I mean, it's great. It's great from an ISA. It's cool. I mean, we both grew up on DEC stuff and 11s, and I actually remember people who were in the game of putting things in the registers on the DEC 10. But I sympathize, but I'm just noting that there are reasons why they actually are not in current modern architectures.
I have heard that reasons, and they do so many clever things with microcode in the x86 is I don't believe it. It sounds like excuses to me.
Okay, it's interesting.
Yeah.
All right, so that's it. Let's give it up for Walter. My main takeaway from that is that we're getting 16-bit floats. So yes, good work.
Yes, at least for the AArch64.